When I put these presentations together, I then realised actually what boring subjects I pick. So I do apologise that I talk about, I think it was people arriving and Poisson processes last year, and this year it's about a global dispatcher interface. But I'll try and make it more interesting than it appears. I'll do my best anyway. So I thought we'd start off by what a dispatcher does. I'm sure most people in the room know what a dispatcher does, but I'll just review the sort of thing that we're talking about when we're talking about talking to a dispatcher. So a dispatcher involves assigning a car to a new haul call. So we've got Fred, he's on the 6th floor and he wants to go down, and he presses a button, and we've got to decide which lift is going to stop, A or B in this instance. And one of the most basic dispatchers is an ETA dispatcher, which basically works out how much time it's going to take until a lift arrives at you. So in this example, we've got Fred again, he's on the 7th floor. And we could either give him lift 1, 2, or 3. The first one is going to take about 15 seconds to get to him, but it's got a car call. That's the yellow dot there. So if you add 10 seconds to stop, that's going to be 25 seconds. The second one is 10 seconds away, and the third one is 5 seconds away, assuming it can stop in time. And on that basis, the ETA dispatcher would allocate the third car. And that's really quite simple. And if that's all we did, then I really wouldn't have a job. But that's a basic dispatching. It actually works really well. But we like to get more enthusiastic and apply advanced artificial intelligence and so on. So you can get things like genetic algorithms. There are many things we could talk about. One of them is genetic algorithms. And that's where we trying to think about natural systems. And we might say genetic algorithm is looking at an allocation where we got 4 lifts and we got 5 haul calls, and how are we going to make a decision? Because there are lots of different options we could have, different possibilities. And in fact, if you had 4 cars and 5 calls, there are 1,024 possible options. So you can imagine if you had an 8-car group and 20 floors or something, all the possibilities you could look at are absolutely enormous. And the theory goes, well, the practicality is you couldn't look at every possible option. So let's try to do something based on artificial intelligence. Genetic algorithms about the idea of natural evolution. And so in this allocation, one of these allocations of an elevator to a haul call corresponds to a gene, and the group together corresponds to a chromosome. And we might start by describing it like this. We've got a set of lifts, and you abbreviate it by here, and that corresponds to a chromosome. It's an allocation of lifts to calls. It's not necessarily the best one, but it is one possibility. And so within genetic algorithms, we select a whole a range of random chromosomes, and then we'll use within our dispatcher a simulation to work out which is the best one. And then what we'll do is then we'll take a couple of good chromosomes that should perform relatively well in our dispatching simulation, and we might say we might try and combine them with random techniques. So we could throw a dice. These are 2 good chromosomes, and we kind of come up with a second generation chromosome, and that's a possibility. We can also do things like mutate them randomly and come up with another chromosome, and we get the next generation approach. We test this generation against the last generation. We just keep on working, and we might have 20 milliseconds to do those calculations, and we just try and evolve the best solution possible. So that's dispatching at a slightly higher level, but dispatching at the higher level just involves a lot of maths. We just have to do a lot of number crunching, a lot of maths, and it gets even more interesting when you do things like have double-deck lifts and destination control. It gets even more interesting when you have 2 cars per shaft, and you've got to avoid the lifts crashing into each other. It's becoming quite an interesting problem now, which is why lots of academics love it. And it gets even more interesting when you do these multiple cars in shafts. Yeah, this is obviously a simulation of a product that someone's developing at the moment. I won't mention the name. And you can see we got all these. we've got all these lifts, and they're all actually each one is dependent on the other one, and there's lots of overlap and going on. So there's quite a lot of processing going on and optimization and trying to get the thing to work efficiently. So if we're going to write software for this sort of thing, and as Adam says, I write simulation software, I also write the dispatching software sometimes that actually controls the lifts. the sort of, this is my favourite description of object orientation. So this is a cat, yeah, and this cat is being interacted with by these scientists, and they know that if you pat the cat, it purrs, and if you kick it, it squeals. Yeah, so you can interact with it, and the thing is, they can examine the behaviour of that cat, but they don't need to know how the cat works. And that's object orientation in the software form. We've got all these components and they interact with each other, but they don't necessarily need to know how the individual ones work. And when we build a simulation, and there are a number of people who've built in this room who've built simulations, we've got these different components. So you might have the people on the left here, then you've got the lift itself, which goes up and down. It's just not aware of anything else. We just tell it to go and serve this call and that call. Then you've got the building, information about the building. And then you've got the dispatcher bit that's doing the sums. And then you've got some results. And I'm interested in, so within my simulation, I'm interested in this dispatcher bit today. And I'm interested in what we're trying to do is, what we've achieved in the past is actually have the same code running in the simulation as we have in the real world. So we just unplug the software people and put in real people. And we have the same code running the same dispatcher, doing the same things. And if it all works well, it all ties up and we can close the loop, the design loop, which is really good. So I'm at the moment focusing on the communication bit between the dispatcher and the rest of the system. So all I'm talking about today is this bit here, yeah, how we talk. As Jonathan talked about just before the break, it's really important that we communicate in a way that's consistent, and it's actually really useful to have standards. Now, within our software, the dispatching interface standard is actually a dynamic link library, and it's actually 20 or so years old. Yeah? So it's based on technology which is that old, so we really need to upgrade it. And there's much better technology than there was 20 or so years ago. So that's why, again, it's one of my interests at the moment. But before we actually think about that dispatcher, we need to make some decisions about what the dispatcher is going to do and how the architecture works. And the first thing we get to is, should we have distributed control or central control? And distributed control is where, which is very common, is where each of the lifts is making its own dispatching bids. So in my slide about ETA, those lifts actually said, I'm going to get there in 25 seconds, or I'm going to get there in 5 seconds. And they all make their bids. And then one of them is the master, and then actually makes that decision, actually says, okay, well, I'm lift 1, but lift 3 did better, so we'll give it to lift 3. And the nice thing about distributed control is that if one lift fails, the dispatcher, the master function of one lift fails, then another lift can take over. Yeah, so basically that lift fails, okay, it was being the master dispatcher controller, but actually another lift can take it over and do it instead. So it's a good, robust system. And this is the alternative, and this is where you basically have one big master dispatcher, and it does the job. The lifts basically give their bids, and it is this separate system the separate system decides which one is going to have the call and does most of the calculations in there. This system, obviously, if that fails, then the whole system falls over, so you should really have a backup to that. Yeah. So and this decision between the two. Now I'm going to come down on one side of those two options, and the reason I'm going to come, well, let's think about where as a dispatcher designer I'm involved. I've got lots of different controllers that want to interface with our dispatchers. So we need to have, if the controller's doing the dispatching, that actually doesn't work. So if I want to do a dispatcher that can deal with a whole series of controllers, I can't have distributed. I have to have centralized. And even if I was doing all of the dispatching for everything, if you have a distributed processing within a system like this, car A has got to talk to car B, C, D, E, F, G, H, I, J, K, and there's a massive amount of data going around the network. And I don't think that works. Yeah? So some of my dispatcher colleagues, past and present, have had this argument over the years. I think I'm winning it, but I'll find out at the end of this presentation. But I reckon I'm going for central control. Yeah, I think actually the dispatcher itself should make, I'm looking at Stefan because we've debated this for years, and Ineer at the back there. I reckon central control is the answer. And we need to have backup systems, so if the one central dispatcher fails, then we can switch over to a backup. That's, before I can do an interface, I have to decide if it's centralized or distributed control. So that's why I need to do that. Then we actually get to who does what in these systems. And again, this has been the subject of debate and argument over the last 20 or so years. It's the dividing line between what the dispatcher does and what the lift controller does. Yeah? So I'm obviously a dispatcher designer, so I think dispatchers should do everything. Whereas people who are involved in controller design think actually, well, we don't want to give too much to the dispatcher. Actually, the controller should do some stuff. So just to give you an idea of basic what typical controller does. So a controller might be given a call by the dispatcher. So let's say the dispatcher has given this lift these 3 landing calls. So what the lift's going to do, it's going to serve this call. And it does this all on its own. It doesn't need a dispatcher. Once it's been given the calls, it can do what it wants with those calls. And actually that works really well. Works really well with an ETA dispatcher. Okay, and so that local logic is dealt with there. But when you start interfacing with lots of different dispatchers, you find there is an enormous number of subtleties in how a controller works. They all follow that basic logic which I just showed you, but there are instances where you actually, as a dispatcher design, you don't know what the lift is going to do. And I'll give you one example. There are many. This is, because we're real-time systems, things can change. So this lift has been given this call 7 down. And as it's travelling there, what it's going to do at the moment is going to stop at level 7, it's going to reverse, and it's going to come down again. Now, while it's still travelling, and before actually it reaches its slowdown point, a new landing call comes in. Yeah, a new landing call comes in. So can the dispatcher give this to car A or not? Well, if it does, it might work. It might be that the controller is fast enough and bright enough to know, actually, I don't want to reverse there anymore. I actually want to go up to here, serve there, and reverse and come back down. Yeah? Or you could end up allocating this call to here. It actually doesn't reverse, so the lift goes to here. And in a destination system, it would then take a whole full round trip until it got back to this call. So things can go wrong. And things do go wrong, and in the commissioning of some of the systems I've been involved in, these subtleties have gone wrong and made a big difference. And unless you spend a lot of time and money really commissioning those systems in detail, you get errors which quite often will remain for the lifetime of the installation, because they're very difficult to find out after it's installed. The other thing that is one of my hobby horses is intelligent door control. And as a dispatcher designer, I happen to know, if I've got destination control, I happen to know that there's probably just one person getting off on floor 5. And if I can control the doors, as soon as the person has broken the beam and then the beam has been reestablished, I can close the doors. Now, almost all destination systems I've ever used, if the dispatcher knows there's only one person, the person goes in, the beams are re-established, and then it waits 2 or 3 seconds until the doors close. Now, those 2 or 3 seconds, I can throw a lot of artificial intelligence at that dispatcher and not get those 2 or 3 seconds back. Whereas if I could control the doors, I could really make a big difference. So I also think the dispatcher should be doing that. So consistency. I want a dispatcher that can do all these things across all systems and not have to be configured to each system, which leads me to the dividing line between a dispatcher and the controller. And when I'm designing a dispatcher these days, I want this to be dumb. I want this to just do what it's told. And I want all the intelligent logic in here, otherwise these two systems fight. And they misunderstand each other. So, wrap up now. I'm not going to go through all the tables, but so what we're moving from a DLL interface to, we're actually using Google Protobuf, but we can have that. We can have the discussion about what's really important is actually what data we're transferring. How it's formatted, who cares? Yeah. So that's what we're interested in. Jonathan talked about static and dynamic data, and that's really important because we don't want to be sending information that actually doesn't change. We only want to send information which is dynamic, and then we can reduce our network traffic. And we've got all sorts of timing issues, which I don't have in simulation. We have in the real world, we have timing issues. In simulation, I can stop the world, do my dispatching, and start it again. In the real world, I can't do that. So there are different things. So I think I deliberately didn't want to have to talk about all these tables, but if you're interested in all these tables, this is the stuff that I think needs to be done and the information that needs to be exchanged. Within a group of about 4 or 5 people, it's probably quite controversial, but hopefully you've got an insight in some of the debates and exercises that we're going through at the moment.
Richard, thank you very much.